Hi, I am Pieter Abbeel. I'm a professor at UC Berkeley where I do research on AI and robotics, and I'm a co-founder of Covariant where we bring AI robotics into the real world. And today I'm excited to share with you some of my thinking on how we can make reinforcement learning more effective. Now, the starting point for me when I thought about this workshop is when I think about the last maybe 5 to 10 years in robotic grasping, to me, the biggest change in my thinking about grasping came about when my former postdoc, now colleague Sergey Levin, in his then work at Google, showed that a data-driven approach to grasping actually could be really effective. Now, really effective, to be clear, I mean, the size of experiments run at Google hasn't really been run at other places, but um, if you want to collect enough data, reinforcement learning can result in some of the best grasping policies we have been able to achieve to date. Now, of course, when you talk with people about reinforcement learning, probably one of the first things they tell you is it's great conceptually, but the sample complexity of the trial and error learning is just expensive. And there's a lot of truth to that. Even for something as simple as the game of Pong, it took 40 days in the DQN paper to learn to play it. AlphaGo Zero required almost 5 million games. And those are games, very restricted situations, not nearly as open-ended as grasping, let alone grasping with a purpose to then do something. Another thing people typically bring up is reward design. It's easy to end up with a optimal policy that is optimal for your reward function, but your reward function was actually not representative of what you wanted. And the canonical example that is often shown here is this boat going in circles in the harbor, even though it's supposed to be participating in a boat race, but the score in the game is such that it's higher reward to stay in the harbor. So I think both of these are still big challenges, but a lot of progress is being made. And I'd like to share with you some of the latest progress data we've made in my lab towards addressing these two challenges. So I'll start with the first one, sample complexity. And the angle I'm going to come from here is the role representation learning can play in reinforcement learning. This is some graphs we were looking at in my lab about a year and a half ago. These are from the D4PG paper. And what we see here is vertical axis is performance, so higher is better. Horizontal axis is number of training steps. So further to the right, the longer the training lasts. So going up quickly is what you want. And so the blue curves are fast learning curves, and the green curves are slower learning curves. What's the difference? They run the same algorithm, but the difference is that the blue curves, the training happens with access to the underlying state of the world. In the green curves, there is no direct access to the underlying state of the world. It's trained with just image inputs. And so we see about a factor 100 difference in how long it takes to learn from images compared to how fast we could learn with direct access to state. Now, of course, in the real world, it's very hard to get access to state. So learning from images is more likely to be practical. And it's important to see what we can do in terms of reducing the sample complexity there. And the question we asked is, can we bring this down to sample complexity of learning directly with access to state? Now, for some of you, this might remind you of the Jan LeCun cake. Jan LeCun gave a keynote at NeurIPS 2016, so quite a few years ago now, saying, hey, look at this cake. Reinforcement learning is just a cherry on the cake. It's small. There's not much there. What he meant with that is there's not much signal there. Icing on the cake is supervised learning because we're willing to label a good amount of data, and there's a lot of signal in those labels. But then the most signal we're going to get ultimately is from unsupervised data, the body of the cake, because there's effectively infinite unsupervised data available for us to train on. And so it was really a call to action, I would say, in terms of when we do things like reinforcement learning, which we ultimately want, we might need other tools to make it succeed in a data efficient way, especially in terms of trial and error learning data efficient. We're happy to take a lot of passive data as needed also. Okay, so how do we bring in unsupervised learning? Well, in computer vision, one of the biggest breakthroughs in unsupervised learning has been contrastive learning, which came out about a year ago with its big breakthrough SimClear, paper by Jeff Hinton and collaborators, showing in this graph here that SimClear can do as well as supervised learning. And SimClear is a unsupervised approach where there is then one linear layer attached to the network here for the supervised training. So the features are essentially all trained unsupervised with then a linear classifier on top of that. This is on ImageNet, and we see SimClear can match the performance of end-to-end fully training a neural network on ImageNet. So that's really interesting. It's an unsupervised approach to get really good features. Well, what's under the hood? Well, this contrastive learning, the way it works is that you take images. Let's say we have two originals, original one, original two, maybe pictures from a bin we want to grasp from. And then the next step is to duplicate them. So we make a duplicate for the first one and then duplicates for the second one. Then our neural network will process each of them individually and generate embeddings. In this case, we end up with 4 embedding vectors. Then contrastive learning operates by saying the embedding vectors that come from the same original should attract each other, and the embedding vectors coming from different originals should be repelling. That's the overarching training objective. It's a bit of detail to it to actually formulate this mathematically, but that's the key idea. And so you don't need to know what's in those images. You just need to be able to generate some duplicates and then have an objective for attracting and repelling. And when you do that, you get these great results shown here. Okay, now let's think about this in the context of reinforcement learning. In reinforcement learning, we collect data. Typically, it goes into a replay buffer. And then when we actually want to process data, there's an encoder, which then goes to the actor and the critic network. But now we're going to attach an extra network for contrastive learning, an extra head. And so by doing that, we can do contrastive learning of representations. And so the encoder will likely largely be trained contrastively, effectively unsupervised, whereas only then the actor and the critic need to be trained with reinforcement learning supervision, that is reward supervision. We need to make a few decisions there. How do we do this when we generate these duplicates? We take frames from the replay buffer, and we generate duplicates by cropping. In our experience, different crops is really key. You can think of this as encoding some translation invariance to how the robot should control itself. Now, another important choice is how do you encode a contrastive loss? Typically, this is done with a softmax. So the top here is the weighted inner product between a query and a key. These are 2 duplicates for the positives, and then normalized by exponentiated inner products of the negatives. The weighting matrix here sometimes is used, sometimes not. In our case, we found it's quite important to have a learned weighting matrix there. And then the third kind of decision point, which again we resolved empirically, is whether or not to use a momentum encoder. And this is the MoCo paper, which introduces that, came around the same time as SimClear, similar results, similar ideas. And again, this actually mattered to us. So we use MoCo. You can see the learning curve is a lot better with a momentum encoding. Okay, with these pieces in place, we run image-based reinforcement learning in the DeepMind control suite and compare it with state-based reinforcement learning. And these graphs here on 16 different environments, ranging from ball and cup, card pull, finger turn, pendulum, reacher, walker, and so forth. The gray curves are when you get to learn directly with access to state. And the red curves are when you learn with only access to images, but using the contrastive approach to more efficiently learn the encoder. And we see here that the red curve almost consistently matches the gray curve, showing that we can learn almost as efficiently with access to images as with direct access to state. So that factor 100 we had initially of less efficiency, we actually were able to bridge that gap. We also compare with prior state-of-the-art approaches for image-based RL. The red curves is us, and we see that consistently it outperforms the previous approaches. The gray curve, again, that is all the way at the top, a little bit ahead of the red curve, is based on access to state. So there's additional information compared to the other approaches. We also looked at the results in Atari games. It's also a vision-based problem, and we compared curl, which is our approach, which we put on top of Rainbow, the state-of-the-art model-free approach, with Rainbow itself, with Simple, which is a state-of-the-art model-based approach, also with human and random. And we see curl Rainbow is really effective in vision-based reinforcement learning on this Atari benchmark. Now, there are a few environments where we still saw a gap. So at the top here, you see some environments where the gray curve indeed outperforms the red curve. So state-based outperforming image-based using curl, the contrastive representation learning. Okay, so we dug a little deeper. We said, what happens if we run reinforcement learning for a very long time? Those are the bottom curves. And we see that the gap remains. And that made us think, well, maybe there's something fundamentally missing in the images, because if we run reinforcement learning long enough, in principle, in the end, it should figure it out, but it's not fully figuring it out. So we're thinking, okay, what can we do to verify this hypothesis that maybe sometimes images just don't have the relevant information or not enough of it? Maybe they don't have contact forces, which are in the state, not part of images, things like that. Well, we said, okay, let's actually run supervised learning from images to the underlying state. And let's plot the errors. And here are 3 environments where the first environment has low error when we go from image to state. Second environment has medium error, and the last environment has large error. We cannot reproduce the state from the image input. And we see the same thing happening in the reinforcement learning, where the harder it is to recover state with supervised learning, the more the gap is when you use image-based reinforcement learning. So we see that when curl doesn't succeed, likely it is because image-based inputs are fundamentally missing some information. Now, another thing we looked at is, what if we run curl, the contrastive reinforcement learning approach I presented, but we don't let the reinforcement learning loss, the actor and the critic loss, propagate into the encoder. So the encoder is fully trained contrastively, no access to the reinforcement learning loss. That's the green curve called curl detached. Red is original curl, and then the others are some comparisons. And what we see here is that the green curve, in say 4 out of 6 cases, is quite close, maybe even 5 out of 6, suggesting that actually often it's not even needed to use the reinforcement learning loss to learn the encoder. It can be often fully learned from just the unsupervised contrastive loss. This inspired us to now go look at what we can do on a real robot. So on a real robot, if we're going to run reinforcement learning, there are a couple of challenges. One challenge, the one we talked about, it's going to be image-based. That's the natural way to set things up, and that could make it slow to learn things. The other thing that could make it slow to learn things is exploration. Is it even collecting the right kind of data? Now, it turns out that we can bypass the exploration challenge by providing a few demonstrations to put the robot effectively in the right ballpark of the kind of things it should be doing. So in our case, we give about 10 demonstrations for each task, which takes us about 10 minutes. Put that in the replay buffer. Then we initialize the encoder with unsupervised pre-training, the contrastive learning I just explained. And then we start reinforcement learning. Now, the reinforcement learning agent in this case has been initialized with these human demonstrations. The representation learning is initialized through contrastive pre-training. And it turns out that the reinforcement learning in the real world with just one robot only takes about 30 minutes for a range of tasks. What are some tasks we looked at? We looked at move. So in move, what we have to do is pick up the blue objects and put it onto the red patch. We gave about 10 episodes of demonstrations. Then after 40 episodes of reinforcement learning, which takes about 30 minutes, it starts having a first success. After 80, it's converged to its optimum. Optimum success rate it achieves here is 26 out of 30. Similarly for pull. So here the task is to reach for an object and then pull it towards the robot. After 5 episodes, it has its first success. After 45, it starts being fairly consistently successful with 28 out of 30 successes in our evaluations. We did not just those 2 tasks. We looked at reach, pickup, move, pull, light switch, and drawer open. And what you see here is when did the first success happen? When did the optimal behavior or near optimal behavior where it feels converged start happening? And what is that level of performance at convergence? We see we reach, often 100% performance. And it takes about 15 to 45 minutes for these different tasks to achieve that asymptotic performance. So this is becoming, I would say, very practical to teach a robot a new skill. You give it 10 demonstrations. You then do some contrastive learning to get a good encoder, and then you run reinforcement learning with the demonstrations in the replay buffer. Okay, so of course there's more to be done, and we want to make this more efficient and want this to be multitask and so forth. But I think there are some really good indicators there that this is becoming more and more practical to do. Now, the other thing, of course, people often bring up is the trickiness with the reward function. How do we make sure the robot actually learns what we want it to learn, not some misspecified reward function? So, reinforcement learning, there are decisions, consequences of actions, and this process repeats. And the reinforcement learning agent will optimize expected reward. Now, here's a result you could get in DeepMind Control Suite. This robot was optimized for as high X coordinate as possible, so running as far forward as possible. It's definitely doing that. Minimizing torque squared, action squared, and minimizing how much the center of gravity deviates from a specific height, 1.3 meters above the ground. Okay, so this is a pretty reasonable objective, I would say. But then when you look at the behavior that comes out, even though it optimizes that objective, it might not be what you want, because it's a bit kind of weird behavior with the arms that now, maybe that's not the behavior you wish it would be learning. Imagine doing something more complex, like specifying a reward function for cooking. Could be really difficult. A lot of things could go wrong before you get it right. Or think again about the boat game where it forgot to race. It was just hitting some interesting bonus targets in the harbor. So what could be an alternative solution? Typically, we have the RL algorithm interact with the environment, and rewards is what's being optimized. But the hypothesis here is that we as humans, maybe we know better what we want than what we put in the reward function. Well, if that's the case, maybe we should participate in the process. And so can we have a human observe the learning, provide feedback in a way that makes it more optimal than what we can put into a reward function? And of course, there's been some work already in this direction, but what we're looking at here is really how we can make this an efficient process. And there are 2 things that we can benefit from here. One thing is that I believe by doing this, a human can teach harder tasks where we can't easily define the reward. It's just difficult to say what exactly should be the reward function, especially because for good learning and reinforcement learning, often we need some reward shaping. We need to say, a reward function that's not just success or failure, because that's hard to learn from. And this shaping is often very hard. And then we can also avoid reward exploitation, where it might, get undesired behaviors if we're not careful. So how do we do this? So our agent will still collect data, put it into a replay buffer. Initially, that won't be the best rollouts because it's just getting started, but hopefully over time, that'll be better and better data, of course. Then we'll collect human preferences. That is, a human will be asked to look at a few rollouts and compare them. Between these 2 rollouts, which one do you like better? Then we'll optimize a reward model using cross-entropy loss. So we'll take this human feedback to learn a reward function. How do we do that? Well, the main idea is here that we formulate this as a classification problem, because we ask the human to classify between 2 rollouts. Which one do they like better? So they classified. So we're going to capture this. we're going to say, okay, the probability of a trajectory 1 being classified as better as a trajectory 2, 0, is going to be proportional to exponential of the rewards along trajectory 1 divided by exponential of the rewards along trajectory 0 plus exponential of the rewards along trajectory 1. So it's a softmax classification model where we expect the human will typically correctly classify the trajectory with higher reward as the one that they prefer. Okay, we can of course then train this classifier to learn a reward function. Then we can use any reinforcement learning algorithm. In our case, we use a off policy algorithm, specifically soft actor critic, to optimize our policy. Then we collect new rollouts, present them to human again, and repeat this process several times. Okay, now if you do this naively and you start out, you'll have pretty random behaviors as shown on the left here, and the human will have a hard time saying which random behavior is preferable over which other. So what we do is we don't start from scratch. We first have some unsupervised pre-training where the robot on its own, without any supervision, without any reward function we specify, is discovering skills. I'm not going to get into the details here, but this approach, active pre-training, actually tries to optimize the entropy of the states visited by the robot. And that'll encourage it to discover diverse behaviors. And then it'll show some of those more kind of consistent, interesting behaviors to a human, and it becomes easier to say, oh, wow, this one's actually more right than this other one. So with this machinery in place, can a human teach our robots novel behaviors? Well, here is the result of 2 teaching sessions. So on the left, it's a teaching session where a human taught the robot, in this case, cart pole, to swing counterclockwise. And on the right, the human taught it to swing clockwise. And the reason we showcase these 2 different behaviors is because we want to showcase that a human can have different preferences, and indeed these preferences will be reflected in the behavior the system learns. Similarly here, when a human trains for lifting the left leg or lifting the right front leg, the robot indeed internalizes that correctly. So human feedback is really listened to and incorporated when it's optimizing its behavior. You can also teach the robot pretty complicated behaviors like backflips. And this a human was able to teach our robot in less than an hour of feedback. Now, the other question we started out with is, can we avoid reward exploitation? Well, let's take a look. Let's go back to the runner. This is a runner that we ran our experiments on. If you just use the standard objective in DeepMind control suite, here's the kind of behavior you could get out. Is dragging this one leg. Sure, it's making forward progress, it's keeping its center of gravity at a good height, but it's not really running behavior or walking for that matter. It's this dragging thing. Then we ask a human to provide feedback during the learning process, and here's what we get. And indeed, the robot has figured out how to properly run. And this was done in less than 20 minutes of human in the loop reinforcement learning. So it's actually very effective to do this. We also, of course, did a more quantitative evaluation. What you're looking at here is learning curves for quadruped, cheetah, and walker. The red curve we think of as the oracle. The red curve is when you run soft actor critic with access to the underlying reward. And then in green is our approach called Pebble, with learning with human feedback. But in this case, to do statistically significant experiments, the human feedback is actually scripted based on the ground truth oracle reward. So that's why the ground truth oracle will always be expected to do better. The green is effectively taught by a teacher that in a scripted way uses the ground truth underlying reward. It's also convenient because that way you can more easily compare. If you want to compare with our experiments, you don't need the same human in the loop. You can use this scripted teacher for running your experiments. And so we see green is actually quite competitive with red, which is really great. Yellow is also our approach where we cut in half the amount of feedback that we allow the human to give, and it's still quite good. And then kind of the yellow greenish is when there's even less feedback, and it still learns quite well. Then black, blue, and purple are when we use PPO instead of soft actor critic, which is a on-policy method, so less sample efficient. Um, and so we see it definitely takes longer there. But again, when we use our human feedback system, in this case, the scripted teacher, of course, we see that the blue curve almost keeps up with the black curve, which is a great sign for our approach. So it's very compatible with both off-policy and on-policy reinforcement learning. But then, of course, the off-policy method is going to be more sample efficient, as we see here. Okay, so in summary, I think reinforcement learning is likely going to be at the core of a lot of future progress in grasping. And I've been thinking this ever since the kind of 2016 results from Sergey Levin and collaborators. And so another interesting thing about that result is that there wasn't that much that was super specific about grasping except for the data collection, but the reinforcement learning was quite generic. And so I think general advances in reinforcement learning will play a pretty important role in the next generation of grasping systems. And so what I was excited to share with you here today are some key recent advances that we made in my lab. One was contrastive unsupervised reinforcement learning, which brings image-based reinforcement learning in terms of efficiency very close to reinforcement learning with access to state, at least in the DeepMind control suite where we evaluated things, but then also made it quite effective on a real robot for a range of tasks. And then the other thing that I think will be really important is to be able to bring a human in the loop in the reinforcement learning process, because reward functions are always very hard to specify really correctly. And so bringing a human in the loop can alleviate that, because the human can provide preferences, can say which of two trajectories they might prefer. And we've shown that that can be learned from very efficiently. In our case, again, this is simulated robots in this experiment so far, but it's showing great signs of life that I think show great potential for in the future putting this on real robots. Thank you.